A signal from Voyager 1, 24 billion kilometers away, arrived after a 22-hour journey through empty space, and what it said made no sense. Not silence, not static. A structured, repeating pattern of 1's and 0's that matched nothing in NASA's codebooks. Their best engineers couldn't explain it for months, and when they finally did, the answer raised a question far stranger than any broken circuit. That repeating pattern of 1's and 0's, the signal the hook described, wasn't random. That's the first thing that unsettled NASA's engineers. Random noise would have been almost reassuring. Random noise means a broken antenna, a dead transmitter, interference from some cosmic source. This wasn't random. The telemetry modulation unit, the subsystem responsible for physically broadcasting Voyager's signal, was still working perfectly. The radio link was intact. The carrier wave was clean. But the data riding inside that wave, the actual content, had collapsed into a looping, repetitive sequence that matched no format in any of NASA's codebooks. It looked, unnerving as this sounds, almost deliberate. To understand why this was so alarming, you need to know what the flight data system actually does. Think of it as Voyager's translator. Every reading from every instrument, plasma density, magnetic field strength, the spacecraft's own temperature, and power levels, flows into the FDS first. The FDS packages all of it into a coherent signal, a structured language Earth can read, and then hands it off for transmission. If the FDS is compromised, you don't just lose one instrument's data. You lose the ability to trust anything the spacecraft tells you. It's the difference between a witness you can cross-examine and a witness who's been replaced by a recording of white noise set to loop. The engineering team at JPL ran through the obvious explanations first. A cosmic ray strike, a high-energy particle punching through the electronics, could theoretically scramble a computer. They couldn't rule it out. NASA said it was equally possible the chip had simply worn out after 46 years. A software command error, something sent from Earth that had accidentally corrupted the system? They checked every command log. Nothing. Antenna misalignment, meaning Voyager had simply drifted off angle and was broadcasting into empty space. The signal strength said otherwise. The spacecraft was pointing correctly. It was talking. It just wasn't saying anything coherent, and every attempt to diagnose it carried a brutal cost. Because Voyager 1 is one of only 2 human-made objects in true interstellar space, past the heliopause, in a region no probe before it had ever survived long enough to study. A radio signal traveling at the speed of light takes over 22 hours just to reach it. Then you wait another 22 hours for the response. Every single question the team asked Voyager cost them nearly 2 days. Every hypothesis, every test, every poke at the system, a 45-hour round trip, minimum. Months of this. Months of 2-day silences between question and answer, while the repeating pattern kept arriving on schedule, punctual and meaningless. Then in March 2024, the team sent a specific command, essentially a request for Voyager to dump its entire memory back to Earth. They waited. 45 hours later, the answer came back, and buried inside it was the answer they'd been searching for. A single chip inside the FDS had failed. Not wiped clean, not destroyed. The chip had failed, stopped working entirely, and that chip happened to hold a section of the FDS's own operating code. The code the system needed to assemble and package data, which meant that for months without anyone on Earth knowing, Voyager had been routing all of its science and engineering output through that damaged section. Every reading from interstellar space, every measurement from instruments operating in a region of the universe no probe had ever mapped, had been passing through broken software and arriving on Earth as nonsense. Fixing a corrupted chip on a 47-year-old computer 24 billion kilometers away is only half the story. Because once they did, what Voyager started reporting about the space it's moving through made the hardware problem look simple. That 45-hour wait between question and answer, Could you have held your nerve through months of that, or would you have called it unrecoverable? Drop your answer in the comments below, because once the team cracked the hardware mystery, what Voyager actually found out there made the wait feel worth every second. The patch held. On April 20th, 2024, after a roughly 45-hour round trip across interstellar space and back, a signal came back from Voyager confirming the fix had worked. The fragmented code, stitched into spare corners of a 47-year-old computer with less total memory than a low-resolution thumbnail image, was running again. The instruments were alive. The data was flowing. NASA's team exhaled for the first time in 5 months. And then they started reading what Voyager was actually saying. The interstellar medium was supposed to be an almost impossibly thin fog, a diffuse mixture of plasma, dust, and magnetic field lines so spread out that it barely qualifies as matter at all. The models physicists built before Voyager crossed the heliopause described it as calm, relatively uniform, a quiet backdrop against which the solar system sits like a bubble. The heliopause, that boundary where the sun's outward pressure finally loses its grip, was expected to be a clean, roughly symmetrical edge, and the medium beyond it was expected to behave predictably once you were past the turbulence of the crossing itself. What Voyager's instruments found instead was something far stranger. The plasma density doesn't sit still. It fluctuates, and not randomly. The fluctuations appear in patterns that the standard models of the very local interstellar medium don't fully account for. Cosmic ray intensities, the high-energy particles streaming in from the galaxy, spike and drop in ways that suggest the region Voyager is moving through is more structured, more layered than anyone predicted. And the magnetic field, instead of holding a steady orientation the way the models assumed, it has been rotating, shifting in ways that recent research published in 2026 is still actively working to characterize. Voyager was sitting roughly 167 astronomical units from Earth, deeply embedded in what scientists are now calling the perturbed interstellar medium, a zone still measurably influenced by the sun's presence in ways that blur the line between solar territory and true interstellar space. Then there's Voyager 2. It crossed the heliopause in 2018, entering interstellar space from a different angle entirely. The plan was that 2 probes would give scientists a stereo view, 2 data points to triangulate the shape of the boundary and the medium beyond it. What they got instead was a puzzle. The readings from the 2 spacecraft diverge in ways that suggest the heliopause isn't the clean, symmetrical shell the models drew. It appears to be asymmetric, dynamic. The boundary itself seems to shift depending on where you cross it, which means the map of where our solar system ends and interstellar space begins is less a fixed line and more a living, irregular edge that changes over time. That's the thing that keeps scientists up at night. Not the broken chip, but what the working chip revealed. The corrupted FDS was a hardware problem. Hardware problems have solutions. You find the bad code, you fragment it, you reroute it, you wait 45 hours, and either it works or it doesn't. That's engineering. What Voyager is measuring out there in the dark, the turbulence, the shifting fields, the structured density patterns in a medium that was supposed to be featureless, that's physics we don't yet fully have the language to describe. Voyager 1 is still moving, 17 kilometers per second, deeper into that perturbed and poorly understood medium, its 2 remaining instruments still ticking, still measuring, still transmitting. A 47-year-old machine built on 1970s silicon, running patched software fragmented across whatever memory it has left. And it is teaching us, piece by piece, that the map we drew of interstellar space was, at best, a rough sketch of something far more alive than we imagined. Subscribe if you want more like this, and watch the next one now.